The African elephant is the largest land animal alive today. 6 tons, 4 meters tall. Magnificent. It represents the absolute limit of what mammals can achieve on land. Get any heavier, and the engineering breaks down. Now meet Argentinosaurus. 70 tons, 12 meters tall at the shoulder, 35 meters long. 10 elephants, combined. Its heart had to pump blood 12 meters straight up to reach its brain. The pressure required? Over 600 millimeters of mercury. Enough to burst every artery, destroy every organ. According to everything we understand about vertebrate physiology, this animal should not exist. There's a reason land mammals never exceeded elephant size. It's not lack of trying. 30 million years ago, Paraceratherium, the largest land mammal ever, reached 15 tons. Twice the size of an elephant. 1/5 the size of Argentinosaurus. The problem is physics. As animals get bigger, their mass increases with the cube of their dimensions. Double the height, weight increases 8-fold. But bone strength only increases with cross-sectional area, the square of dimensions. This is the square-cube law. Galileo figured it out in 1638. If you scale up an elephant to sauropod size using the same body plan, the legs would shatter under their own weight. But it's not just bones. Mammals face 3 fundamental barriers to gigantism. First, mastication. Mammals chew their food extensively. Large herbivorous mammals spend up to 18 hours a day eating. Elephants process about 150 kilograms of vegetation daily. They chew it, extract nutrients, move on. The head must be heavy, filled with massive grinding teeth and powerful jaw muscles. Scale that up to sauropod size, you'd need a head weighing 3 tons. At the end of a neck extending 12 meters, the leverage would be impossible. The neck would collapse. Second, viviparity. Mammals give birth to live young. Pregnancy. An elephant carries a single calf for 22 months. The calf weighs 100 kilograms at birth. Now imagine a 70-ton mammal trying to gestate offspring. The metabolic cost would be staggering. The size of the fetus would limit how large the mother could grow. Viviparity creates a ceiling, a maximum size beyond which the reproductive burden becomes impossible. Third, respiration. Mammal lungs work on tidal ventilation. Air flows in, air flows out. Same path. It's adequate for mammals. But scale it up to sauropod dimensions, you'd have a trachea 9 meters long. Every breath you'd inhale and exhale through that tube. The problem? Dead space. The air in your trachea doesn't reach your lungs. It just sits there, stale, oxygen depleted. For a 30-ton sauropod with mammalian respiration, the dead space would be 184 liters. So large that stale air would be sucked back into the lungs instead of being expelled. You'd suffocate on your own breath. So the question isn't, how did sauropods get so big? The question is, how did they bypass the mammalian wall? And the answer is, they weren't mammals. Sauropod dinosaurs were the largest animals ever to inhabit land, with body masses reaching 50 to 80 metric tons, surpassing the largest terrestrial mammals and non-sauropod dinosaurs by an order of magnitude. From their beginnings in the late Triassic, 210 million years ago, sauropods diversified into about 120 known genera and dominated ecosystems for more than 100 million years. 100 million years. Mammals have only been the dominant large herbivores for 66 million years. Sauropods have them beat by 34 million years, and counting. They lived on every continent, in forests, plains, even deserts, from pole to near pole. So, how? How did evolution solve problems that physics says are unsolvable? The answer is a cascade. Not one breakthrough, but a series of them, each innovation enabling the next, each one removing a constraint that held mammals back. They didn't chew, they didn't give birth to live young, and they didn't breathe like you or me. The forensic evidence is written in their bones, in their eggs, in the microscopic structure of their vertebrae. Let's start with the head. This is the skull of Diplodocus. The animal was 26 meters long, weighed 15 tons. Its skull? 60 centimeters. About the size of a horse's head. A horse skull, on a body 10,000 times heavier. It's ridiculous. It's brilliant. Mammals are limited by their extensive mastication. Chewing requires massive heads, powerful jaws, and constant energy expenditure. Sauropods? They didn't chew at all. Look at these teeth. Peg-shaped, spoon-shaped in some species. They're not built for grinding. They're built for stripping. A sauropod would clamp its teeth around branches, pull back, strip the leaves, swallow them whole. No chewing, no grinding, no breaking down cellulose mechanically. Instead, they swallowed rocks. Gastroliths. These sat in their massive gut, a fermentation chamber, grinding food internally. Bacteria did the rest, breaking down cellulose, extracting nutrients. The advantage? Massive. Chewing is expensive. Jaw muscles consume energy. Heavy heads need thick necks. Thick necks need massive bodies to support them. By eliminating mastication, sauropods could have lightweight heads, long, graceful necks with minimal musculature, drastically reduced energy expenditure on feeding. A small head means you can have a longer neck without it becoming a structural nightmare. The leverage problem disappears. Think of it like a crane. The lighter the load at the end, the longer the arm can extend. Sauropods had the lightest possible head for a herbivore, which meant they could browse higher than any competitor. 35 feet in the air. Tops of conifers. Araucaria trees. Vegetation no other animal could reach. This is selective advantage. Height equals access. Access equals survival. And survival drives body size increase. But a long neck and small head solve only one problem. What about reproduction? This is a sauropod nesting ground. Discovered in Patagonia, hundreds of eggs, arranged in clusters. Each egg about the size of a basketball, for an animal weighing 70 tons. An elephant calf is born weighing 100 kilograms, about 1.5% of the mother's mass. A sauropod hatchling? Maybe 5 kilograms? Less than 0.01% of adult mass. Mammals are limited by viviparity. Giving live birth imposes metabolic costs and size restrictions, as fetuses must be carried to term. Sauropods laid eggs. Oviparity. And that changed everything. Advantage 1. No gestation burden. The mother invests energy in producing the egg. shell, yolk, nutrients. Then she lays it, moves on. The developing embryo is external. No 22-month pregnancy. No carrying a multi-ton fetus. Advantage 2. Quantity. Sauropods could produce multiple offspring with minimal individual investment, unlike mammals constrained by live birth. Lay 30 eggs. Some get eaten by predators. Some don't hatch, but a few survive. That's enough. Advantage 3. Start small, grow huge. Because the hatchling is so small relative to adult size, sauropods could grow across a vast size range, from 5 kilograms to 50,000 kilograms, a 10,000-fold increase. They didn't grow slowly like mammals. They grew fast. Bone histology reveals rapid, sustained growth rates in juvenile sauropods, reaching adult size in decades rather than centuries. We can see this in their bones. Lines of arrested growth, like tree rings. Some sauropods reached full size in 30 to 40 years. An elephant takes 15 years to reach full size, and it's only 6 tons. Sauropods were adding tons per year. And here's the fascinating part. Juveniles and adults occupied completely different ecological niches. A 100-kilogram juvenile ate low shrubs, ground cover. A 50-ton adult browsed treetops. They weren't competing with each other. They weren't even eating the same plants. The evolutionary cascade model posits that sauropod gigantism resulted from the unique historical interplay of plesiomorphic and derived traits, with each innovation enabling the next. No chewing, small head, long neck, high browsing. Egg laying, rapid growth, vast size range, niche partitioning. But even with all this, there's still the blood pressure problem and the suffocation problem. How do you pump blood 12 meters upward without destroying your own arteries? How do you breathe through a 9-meter-long neck? The answer was hidden in their bones. Let's talk about giraffes first. They're the tallest living land mammals, head 6 meters above the heart. To pump blood that high, giraffes have blood pressure around 280 millimeters of mercury, nearly double human blood pressure. And they need extreme adaptations to handle it. Thick arterial walls, tight skin on the legs to prevent pooling, special valves in the neck veins. Even then, they're at the edge of what's physiologically possible. Now imagine a sauropod, Brachiosaurus, head position 12 meters above the heart. Pumping a vertical column of blood 8 meters above the heart would require arterial blood pressure exceeding 600 millimeters of mercury. 12 meters? You're looking at 800 to 900 millimeters of mercury. That's not sustainable. No known animal can survive that. The arterial walls would rupture. Organs would hemorrhage. So, some researchers argued, sauropods must have held their necks horizontally, never raised them, like this, sweeping side to side to browse. Phylogenetic bracketing and physiological arguments suggest that all dinosaurs had a 4-chambered heart with complete separation of pulmonary and body blood circulation, enabling them to generate necessary blood pressure. But there's another solution, one that doesn't require us to ignore biomechanical evidence for vertical necks. What if they didn't maintain that pressure constantly? Diverse lines of evidence suggest giant sauropods were probably warm-blooded and metabolically active when young, but slowed their metabolism as they approached adult size, which diminished the load on the circulatory system. This is called gigantothermy. When you're small, you lose heat quickly, high surface area to volume ratio. You need a high metabolism to stay warm. But when you're massive, 50 tons. Your core temperature stays stable just from your sheer bulk. Heat generated by cellular metabolism gets trapped inside. You don't need to be warm-blooded anymore. A 70-ton sauropod would take weeks to cool down or heat up significantly. Its internal temperature would remain stable regardless of external conditions. And here's the advantage for blood pressure. If your metabolism is lower, your heart doesn't need to pump as vigorously. Blood flow can be slower. Pressure can be lower. Maybe adult sauropods didn't hold their necks vertically for extended periods. Maybe they raised them briefly to reach high branches, to scan for predators, then lowered them. Models suggest sauropods could have tolerated intermittent high blood pressure if the neck was raised only occasionally, allowing arteries to recover between episodes. Like holding your breath. You can do it for a minute. You can't do it for an hour. But metabolism and blood pressure are only part of the story. The real breakthrough was how they breathed. Among extant air-breathing vertebrates, the avian respiratory system is the most efficient gas exchanger, with lungs serving as gas exchangers and air sacs operating as ventilators. Birds don't breathe like mammals, and neither did sauropods. In mammals, air flows in, air flows out, tidal ventilation. In birds, air flows in one direction, always forward, through the lungs. Here's how it works. Birds have air sacs, 9 of them, distributed throughout the body. These sacs don't exchange gases, they're bellows, pumps. Breath 1. Air enters, flows through the lungs into the posterior air sacs. Breath 2. Air from the posterior sacs flows forward through the lungs again, extracting more oxygen, then into anterior sacs and out. The lungs are always exposed to fresh, oxygen-rich air. No mixing with stale air, no dead space problem. This unidirectional flow means birds extract oxygen far more efficiently than mammals, essential for the energetic demands of flight. And sauropods had the same system. Look at these vertebrae. They're not solid, they're filled with chambers, pockets, intricate internal architecture. These pneumatic features are osteological correlates of air sacs, thin pulmonary protrusions that invaded the bones. We see this in cervical vertebrae, thoracic vertebrae, even some ribs. The pattern matches exactly what we see in birds.
Calculations for Apatosaurus show that with a mammalian respiratory system, its tidal volume would have been less than its dead space, meaning it would suffocate. But with an avian system, it could breathe efficiently despite a 9-meter trachea. Remember the dead space problem, the 9-meter trachea? With unidirectional airflow, it doesn't matter. Fresh air is always flowing through the lungs. The trachea is just a conduit. Stale air never gets sucked back in. The air sac system also reduced body density through skeletal pneumaticity, making the skeleton lighter without sacrificing strength, crucial for supporting gigantic bodies. And there's another advantage: cooling. That rapid airflow through the air sacs, it's a cooling system. A massive sauropod generates enormous metabolic heat. The air sac system helps dissipate it. So now we have the complete solution. No chewing, small head, long neck. Egg laying, rapid growth, gigantism. Avian respiration, efficient oxygen delivery, dead space problem solved. 4-chambered heart plus gigantothermy, blood pressure manageable. Evolution didn't break the laws of physics. It found a different path around them. A path mammals never discovered. But there's still a mystery. Were they warm-blooded or cold-blooded? It's not a simple question, because the answer might be both, depending on age. The evidence is contradictory. Bone histology shows rapid growth in juveniles, suggesting high metabolic rates, typical of endotherms.
Young sauropods were probably warm-blooded, active, fast-growing. But as adults? Some evidence suggests they might have been closer to ectotherms, cold-blooded. Not because they couldn't maintain body temperature, but because they didn't need to. Gigantothermy means your mass alone keeps you warm. A 50-ton animal in a tropical Mesozoic climate would maintain a stable core temperature, around 35 to 40 degrees Celsius, without needing a mammalian metabolism. Evidence suggests adult sauropods may have slowed their metabolism with age, reducing circulatory demands and allowing survival with lower blood pressure. Lower metabolic rate means less food required, critical for an animal eating hundreds of kilograms daily. Lower blood pressure needs, reduced heat stress. And here's interesting, sauropods are rarely found in high-latitude deposits. Fossil distributions suggest sauropods avoided cold climates, preferring tropical and subtropical zones. If they were fully endothermic, mammal-like, they should be able to handle cold. But if they relied on gigantothermy, they'd need warm climates to avoid cooling down over months. The debate continues. Maybe they were mesotherms, somewhere between warm and cold-blooded. Maybe their metabolism shifted throughout life. Maybe different species had different strategies. We don't know. And that's okay. Science doesn't always provide immediate answers.
So what was the upper limit? How big could a sauropod actually get? The largest known sauropods include Argentinosaurus and Patagotitan, estimated at 70 to 77 tons, though fragmentary remains suggest some may have exceeded 80 tons. But could they have gone bigger? Biomechanical analyses show that even with specialized adaptations like soft tissue footpads and columnar limbs, bone stress approached safe limits in the largest species. The bones were under immense pressure. Any larger, and they might have suffered stress fractures constantly. Blood pressure would have been a constant challenge. Even with low metabolism, pumping blood through a body that massive requires enormous cardiac output. And the respiratory system, despite being avian-style, has limits. Air sac volume can only scale so far. Most paleontologists think 80 to 100 tons represents the practical maximum for terrestrial animals. Beyond that, you're fighting physics too hard. And there's another limit. Why get bigger? Body size increase is driven by selective advantages: predator defense, resource access, thermal regulation. But once you reach a size where predators can't threaten you, and you can access all available food, the advantage diminishes. At 50 tons, no theropod is hunting you. At 70 tons, you're definitely safe. Going to 100 tons? Diminishing returns. For 150 million years, sauropods were the architects of their ecosystems. Their high browsing created unique forest structures: lower canopy clear, high canopy dense. They shaped the evolution of Mesozoic plants. Small theropods hunted in their shadow. Ornithischians browsed the understory they couldn't reach. Entire ecosystems organized around these giants. Then, 66 million years ago, an asteroid ended it. The last sauropods were titanosaurs. Some surprisingly small, only 6 to 8 tons. Others still massive, 40 to 50 tons. They survived until the very end, and then they were gone. Today, the largest land animals are elephants, 6 tons, 1/10 the size of Argentinosaurus. Mammals inherited the Earth, but they never matched sauropod gigantism, because they don't have the cascade. The only living dinosaurs are birds, and they carry the air sac system in their DNA. When an eagle breathes while flying at 10,000 feet, It's using the same respiratory system that powered the largest land animals ever to exist. The impossible giants are gone, but the innovations that made them possible, those are still here, soaring above us. Evolution doesn't break the rules. It rewrites them. No chewing, egg-laying, avian respiration, Gigantothermy. Not one miracle, a cascade of innovations, each removing a constraint, each enabling the next. Mammals hit a wall at 15 tons. They're still hitting it today. Sauropods sailed past it by a factor of 5. We're still discovering how they did it. New fossils reveal new details. Recent 3D morphometric studies show that wide-gauge posture and specialized limb morphology were crucial exaptations that enabled extreme gigantism in titanosaurs. Every answer raises new questions. Were they warm-blooded or cold-blooded? How high could they really raise their necks? Could they have gotten even bigger? For 150 million years, they defied what we thought was possible. They were engineering marvels, biological impossibilities made real. The next time you see a bird take flight, remember, that respiratory system, the most efficient on Earth, wasn't designed for flight. It was designed for giants. It just happened to make flight possible later. Evolution is an engineer, not of single solutions, but of cascades. And sometimes those cascades create giants. This is Cosmic Canvas, where even evolutionary hallucinations are taken seriously, because what looks like biological contradiction might be nature's deepest insight. Until next time, stay curious, stay humble, and remember, if nature built something that should have been impossible, it didn't cheat. It discovered something we missed.